Hi everyone, today's lesson is on arcs and chords and inscribed angles. And so we're going to get started. Given a diameter AB, so this is a diameter and it's perpendicular to this chord, which is CD. What conjecture would you have about this picture? What do you think? Hopefully what you're coming up with is that this length right here, PB or AB, is perpendicular to CD, then that cuts that in half, that chord gets cut in half if it's bisect, if this segment, this radius is perpendicular. In addition to that, this arc right here, if this, let's say, was 120 degrees, that also would be bisected, so that CB is congruent to BD, so meaning those would also be 60 degrees. In addition to that, if we drew in another radii and another one even over here, and we know that this arc, if we were given that was 120 degrees, that would make this central angle also 120 degrees. And then because this is bisecting my chord, it also is bisecting this angle, my central angle, where that would be 60 degrees. And then we have a 30, 60, 90 triangle, which you got a lot of stuff that you can do with that. So a diameter that is perpendicular to a chord bisects the chord, and it also bisects the arc. Okay. There is a proof on this. If you wanted to prove this is a diameter. We talk about them being perpendicular. We know that PC, this length here, is congruent to PD because all radii are congruent. Okay. In addition to that, we know that angle PXD and PXC are right triangles based on they're congruent triangles, right triangles that are congruent, form perpendicular lines based on the perpendicular line theorem. We also know that PX is going to be congruent to itself. So what we have here is a right angle with a hypotenuse and a leg, which means these two triangles are congruent by hypotenuse leg. In addition, we can now say CX is congruent to XD by CPCTC, and therefore AB bisects chord CD. So that's a proof. You could do that. That's not difficult. Based on everything that we've learned, that's one of the rather easy proofs that we've done. The theorem, and in the same circle, now moving on with our chords, they are bisected. If you have this length here, this is going to be congruent to this right here. Likewise, CY will be congruent to YD. But this theorem says in the same circle or in circles that are congruent, chords that are the same distance, and we call that equally distant. So this chord that are equally distant from each other, the center, are also equally distant, meaning this is going to be congruent to this. So if, let's say, my chord CD was, let's say, 10 centimeters, and AB was also 10 centimeters, the lengths are the same, that would mean that these distances would also be the same. And always, the converse, of course, is going to be true, that if I said that there's my center and this distance from here to here, which was perpendicular, was, let's say, 5, and this distance here, which is perpendicular, which is also 5, if these distances are congruent, that would make my chords also congruent. And remember that if my chords are congruent, then the arcs, the intercepted arcs here, are also congruent. They would be the same measurement. So naming all the congruent chords in this, we know that, what do we know? We know that 50 plus 20 is 70. So we can say that arc PS is congruent to, this is from here to here is 70. Then from here to here is 70. So we can say that that's congruent to RQ. Now, all the way around the circle is 360. So let's just do some verification. Let's see, we've got 70 plus 60. We have 70, we have 60, we have 20 and 50, which is another 70. So 70 and 70 is 140. 140 plus 60 is 200 degrees. So if I subtract 200 from that, I get 160 degrees. So this arc out here is 160. So do we have any other? We could say that this arc here, which goes from SPQ, so we can say arc SPQ is congruent to arc RQP. RQP. Okay, and that's all we can say with that. Now, for this problem, I actually would like you to draw this yourself and try to come up with a picture. You'll see something very similar to this in your homework and possibly on a test also. It says a plane intersects a sphere. Remember, spheres are three-dimensional. So try to draw those like that. From the center of the sphere. So a plane, not an airplane, but a plane, like a plane, intersects. And the radius of the sphere is 5. The plane intersects the sphere 3 centimeters from the center. I'd like you to take a moment and try to do that. So hoping that you pause the video and you work that out. You probably got something like this. And so what you're trying to do is you're trying to find what is the radius of the circle that intersects that. So see how it's sliced like that circle? I want that radius. So we know that that's a 3, 4, 5 triangle. So x is equal to 4 centimeters. For this problem, your job is to find the measure of arc AD. So if I want to find this arc, which is here to here, a couple of things. First of all, you have some information that you really don't need. You don't need any of this. So I'm just going to omit that because it's not necessary. So we know that all the way around a circle is 360 degrees. We have a 30 degrees, 150, and 120. Adding those all up, 5, 8, 9, 10, we have 300 degrees. We know all the way around the circle is 360, therefore that's 60 degrees. So for these two, we know we're trying to find PR, arc PR, and arc RQ, which, by the way, are going to be the same because, the chords, remember, if the chords are congruent, then their arcs that intercept them are also congruent. So if all the way around the circle is 360 degrees, and I'm going to subtract 130 degrees, I'm going to get 230 degrees. So from P all the way around to Q is 230 degrees. And I do need to now divide that by 2 because these are two chords and the arcs are of equal measurement. So if I divide by 2, I'm going to get 1/15. So those each are going to be 115 degrees. For this problem here, you know that the sides are congruent. If these chords are congruent, that means the arcs are congruent. All right. If the chord's congruent, the arc's congruent. So that means if this is 80, this is also 80 degrees. And if all the way around my circle is 360 degrees, I'm going to take out the 2 arcs that I have, which is 160, 80 times 2, and I get 0, 0, 200 degrees. So that means that this arc here and this arc here are both 100. So JK is 100 degrees. LM is 100 degrees, and KL, that one, is 80 degrees. Q is the center, and the radius of the circle is 17, so I'm going to attach this right here, being 17. It says that PR is 8 units from the center, so there's our 8. Find PR. Well, this is a Pythagorean triplet. If you don't know your triplets, which makes that 15, by the way, if you don't know your triplets, you would go 8 squared plus x squared, this being x, is equal to 17 squared, and then work that out until you got x equals 15. Okay, so SR is 15, which means this is also 15. So that means the measure of PR is equal to 30. Q is the center. BQ is 3, AC is 8, which makes this 4. Let's draw in our radii. Always draw in your radius when you see your chord attached. That's a 3, 4, 5 right triangle Find the radius. Radius is 5. O is the center, and HG is 12 root 2, okay, which makes that 6 root 2, because that's half of 12 root 2. OM is 6 root 2. Oh, so both of my sides are the same, which therefore, if it's a right triangle with two sides the same, what makes it isosceles, of course, but it also means that these are 45, 45, 90, which in a right triangle, if we have a 45, 45, 90, we know that you have x, x, and this length over here is going to be x root 2. So this is my x, 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 root 2. So 6 times root 2 times root 2 is 2. 6 times 2 is 12. So OG is 12. They didn't want that. What did they want? Oh, okay. So okay is, what is okay? 6 root 2. And OF, which is my radius, is 12. Sketch a circle R, okay, that has a radius of 5 root 2. Now, part of what you're going to have to do on your exam is be able to draw your shapes, and from basically information, some sort of direction. We also have chord XY, and that chord is 5 units from the center. I want you to be smart in how you're going to draw your shapes. Now think about this. Chord XY. There we go. There's X, there's Y. And that chord is 5 units from my center. Okay. Now, what I want you to understand is drawing my chord over here is not attached to my radius, is not beneficial for solving the problem. So the best case scenario here is to attach your radius, which is 5 root 2, to your chord. You know that because this is the distance here, that it does bisect it. That's equal to that. That makes this a right triangle. We have 5, 5, 5 root 2. That has to be 5. It's a 45, 45, 90. So what do they want to know? Find the length of XY. XY is going to be 10. So the measure of XY is equal to 10. Now we're going to move on to constructions of our inscribed and circumscribed circles. Now we've already done our chapter on constructions, which was super fun, but we're going to start talking about inscribed circle or inscribed parts, angles, and whatnot in just a minute. What I want to talk about right now, before we go to the next page, is this. There are 2 ways to say this shape. So what this looks like is a circle that's inscribed in a triangle. You also could say you have a triangle circumscribed about a circle. For this one, you've got a circle that is circumscribed about a triangle, but you could also say you have a triangle inscribed within a circle. So there's a couple ways to say that. For these constructions, if you want to do these, inscribing a circle into a triangle, you would bisect each of the angles, and right, you'd bisect all the angles, and then you would find the point in the middle, which is called the incenter, and then you would arc around. For a circumscribed circle, you would basically use perpendicular bisectors, okay, and find the perpendicular bisectors for each one. Put your point on the vertex and then swing that circle around. Okay, that was from our constructions chapter. So an inscribed angle is an angle whose vertex is on the center or is on the circle. Now there's your center. It's not on the center. It can intersect the center, but it's not on the center. And whose sides contain chords. So we've got a chord, we've got another chord. See how my vertex is on the circle? We call that an inscribed angle. Where before, remember when we were talking about a central angle? A central angle has the center or the vertex on the center. See that? That angle was 50 degrees. That arc that it intercepts is also 50 degrees. Whereas if you have an inscribed angle, if this angle is 50 degrees, the arc that it intercepts is double that. So it would be 100 degrees. Okay, so again, the arc that intercepts it. So if that was the center, so let's say my inscribed angle looked like this, and this was 40 degrees from here to here, that would make that 20 degrees. Likewise, if I had this, if I used the previous example and I did something like this, and I said this arc that it intercepts is 50 degrees, this arc or this angle down here would be half of that, and that would be 25 degrees. And remember what I said is that my inscribed angle could definitely go through the center, okay? It just means that whatever this arc is here, let's say it's 80, this intercepted arc is 80, my angle is half of that, so that's 40. So measure of an inscribed angle theorem means that the measure of the inscribed angle, which is here, so the measure of angle 1 is equal to half of the intercepted arc. So we'll say that's half of PS. So if PS is 60 degrees, this angle in here is 30. A two inscribed angle corollary basically said that if this is 100 degrees from P to S, see how both of these angles inside, they're both inscribed angles, but see how they're intercepted arcs? If I personally like to draw these right on top of my circle and extend my arc and extend my angles out, because that just shows me where my inscribed angle or where my arc is intercepted. So if that's 100, that makes this little angle in here 50. That's my inscribed angle. Likewise, you see how this for R also intercepts in exactly the same place. What that means is it's intercepting the same arc, which means that's also 50 degrees. So this is something that we've done in class. So this shouldn't be anything new. But if you have an angle that has a diameter that is my hypotenuse, then not only are radii congruent, but if we're talking about inscribed angles, see how this angle would go out like this, okay? The intercepted arc that it has is 180 degrees, which means that this would be a 90-degree angle. And what that basically means is any angle that is drawn in with that intercepts at my diameter like this, each one of these, every single one of these would be a 90 degree. And that also goes this way too, okay? Every one of these goes like that. Now, we have another corollary called the inscribed quadrilateral corollary, which basically says if you have a quadrilateral, that's just a four-sided shape. It doesn't mean that opposite sides are congruent. It doesn't mean that opposite sides are parallel. That would be a parallelogram. It means that just a four-sided shape is inscribed in a circle. Then the opposite angles are supplementary, meaning if that's 100 degrees, that would be 80. And if that was 130 degrees, that would be 50. The opposite angles are not congruent. They can be, possibly, but they are supplementary. So we have another theorem that says the chord and the tangent theorem. It's very similar to our inscribed angle theorem, whereas if we have a chord, there's my chord, and my tangent, there's my tangent, then the arc that is formed is this angle here formed by this arc is half of that arc value. So if that's 140 degrees, this is 70. And so again, just reiterating, if I have a chord and I have, let's say, an arc or a tangent, and let's say this from here to here is 300 degrees. From here all the way around is 300 degrees here. This is half of that. So that would be 150 degrees. So some reviewing, AOB is equal to the measure of arc, AB, angle 1, ABC, is equal to half of arc AC, the measure of arc AC. Likewise, the measure of ACP is equal to half the measure of arc AC. And I don't know if you can see that, so I'm going to push that up. All right, so lastly, we have a few more theorems, and that talks about angles that are in our circle, okay? We have angles that are inside the circle that have vertices inside and vertices outside, and they're very similar to our lengths of segments. So I just want to talk about that because you're going to see very similar pictures. So if I were to draw these three circles, now these are circles that we've done before. This was the last section. And the last section we talked about was segments, where we had two chords, and these are all segments. And I just want to do a quick review on that. If I had 5, this is x, this is 3, and this is 7. It would be 5 times x is equal to 3 times 7. The other one we did was if we had two secants, remember that? And we said this outside length times the sum is equal to this outside length times the sum. And then the last one was a tangent and a secant. And we said that this value squared is equal to this outside times the sum. So meaning that would be x squared is equal to 5 times 8 plus 5, which is 13. Now, you would solve for all of those and see the different shapes here. We're going to be using exactly the same shapes with two chords, two secants, and a tangent and a secant. However, what we did before was talk about segments and segment lengths. Today, we're going to talk about angles. Okay, so the first one, now I know this looks very similar, but the first one says that the measure of an angle formed by two chords. Now remember, we're not talking about the lengths, we're talking about the angles, and we're talking about the arcs. If I wanted to find angle 1, and keep in mind, it is not equal to AC, because let's say this is my center here. Angle 1, to find angle 1, it is the equal to the sum, which is going to be arc AC plus arc DB divided by 2. So basically, if this was 50 and this was 30 degrees, if I wanted to find angle 1, so the measure of angle 1 would equal to 50 plus 30 divided by 2. So that would be 80 divided by 2, which is 40 degrees, which would mean angle 1 would equal 40 degrees. So if the two chords intersect inside the circle, then you're adding, it's a sum. But if the two chords, if they're not two chords and they're secants or tangents, then they're outside, and the angle is outside, you're going to subtract. But here, you're going to go 50 plus 30 divided by 2 is equal to the measure of angle 1. So these are the last theorems. I know this has been a lot of theorems. So each of these are exactly the same, okay? Each one of them have the same formula. But one thing of notice is that, see, the angle that I'm trying to find is outside, okay? It's outside my circle. Whereas in the last example in here, the angle that I was trying to find was inside my circle. So the ones that are outside my circle, you're subtracting. So you're going to go x minus y divided by 2. So for example, let's say this is 100 degrees here and this is 20 degrees here. In order to find angle 1, which is outside, you're going to go 100 minus 20 divided by 2 is equal to the measure of angle 1. So 80 degrees divided by 2, which is 40. So therefore, angle 1 would be 40 degrees. Likewise, in order to find this outside angle, you're going to take this arc out here, which is x, subtract the inside arc, which is y, divide by 2. And for these kinds of problems, you're going to see examples like this is 300 degrees, find angle 2. That's all the information you're given. But that being said, you know that this is 300 degrees, and that means this is 60. So 300 minus 60 divided by 2 would equal to the measure of angle 2. All right, and that's how you would find that. Lastly, with this one, 3, again, x minus y divided by 2 is equal to angle 3. So all three of those have the same formula. So this is just a summary of all the different things that we covered today, most of the things we covered today. And so I would just review this, pause, and try to make sure that you understand each of these concepts. We're going to do a few things here. So this one right here, this is our last problem. But for this problem, what I would suggest that you do is take a moment, copy this down if you don't already have it written down somewhere, and copy it down, and then take a moment and figure out what you can figure out. Okay, so I'm going to assume that you did that. And so what I'm going to do is start going through this. This looks like it's a diameter because it does go through the center here. So, and then I know that that means that that's 180 degrees. If that's 90, that makes this also 90 degrees. This is 40 degrees. This is 80. All the way to here, again, is 180 degrees. So 180 minus 120 gives me 60 degrees. That being 60 degrees, I know angle 4 is 60 degrees because that's a central angle. I also know that angle 5, if I look at it this way, see right here, and this way, see how I extend this a little bit so I can see my intercepted arc? If that's 90 plus 60, that's 150. That makes angle 5 75 degrees. In addition to that, I know that if that's 60, that's 120 degrees. We know that OB is connected by a point of tangency to this tangent line BG, which means angle 1 is 90 degrees. And that's a 30, 60, 90. So this angle 3 is 30. I also could have, just for fun, I just want to show you, I also could have done something like this right here. And see how my intercepted, I would have gone 120 minus 60, which is 60 divided by 2 is 30. A few other things. If this is 80, that makes angle 2 40 because that's half. If that's 90 and this is 40, that makes that 50. I know what I want to do. Another thing, instead of just subtracting from 360, because I do have 3 of the 4 sides, I'm going to remember that, see this right here? See, these are my chords. And in order to find this angle here, I'm going to find the sum of 40 plus 90 divided by 2. So 40 plus 90 is 130. 130 divided by 2 is 65 degrees, which makes that 65, which makes that 180 minus 65. All right, so that's all that we have for day 3. We have inscribed angles, we have angles inside circles, we have circumscribed circles, inscribed triangles. We have a lot that we covered, so I hope that helps, and thanks for watching.